have done is FinaGuard AM was evaluated in the PVC application. I was briefing about the significance of antimicrobial additive in case of PVC. So please pardon me if I'm repeating a few things because I'm not really sure where did I start missing out. So in case of bacteria as well as fungi, these are the classes which can use plastic as a food or a substrate to grow on. So the concerns in case of soft PVC typically are antibacterial as well as resistance to fungal growth on the surface. So these two features are typically sought in case of PVC. Now here what we have done is using a typical PVC formulation, we have comparatively studied FinaGuard AM with a biocide. Now this biocide, if you see in PVC, there are, of course, there are multiple types of biocides which are used. However, OPPA, which is arsine based, or there is now an organic class which has come up. Those are all thia or sulfur based kind of biocides which are used. Now, if you see arsine, definitely itself is extremely toxic. And the thia group that is coming up as an organic substitute for OBPA, definitely relatively lesser toxic, but still it has toxicity for aquatic life. So what we are looking at here is still a component which has fair amount of toxicity. Now FinaGuard AM was tested in the formulation with reference to this particular biocide. And here you can see the loading level is higher in case of FinaGuard AM because of the fact that PVC is a polar material. Now this a direct connection with the performance parameters that we typically look at when we talk about migratory type of additives. Now, in case of PVC, we have conducted evaluation by following two test methods. First is antibacterial, the same as polyolefins, and the second is resistance to fungal growth. So ASTM G21, which helps to determine the resistance to fungal growth. Now, FinaGuard AM has shown promising results in both the test methods, antibacterial as well as the resistance to fungal growth, as compared to the conventional biocide in plasticized PVC. Now, this is a very important slide. This talks about the performance determining factors for migratory type of additive. Now, FinaGuard AM is an additive which is to be incorporated in the polymer by using suitable compounding technique, and it migrates on the surface when incorporated in the end product. It forms a uniform layer on the surface of the polymer product, and then it imparts the functionality. So it's extremely critical to ensure that there is sufficient amount of additive present on the polymer surface. Now, this typically depends on multiple factors, multiple thermodynamic as well as kinetic factors. One is, of course, the polarity of base polymer. It's also important to understand what's the extent of crystallinity the polymer is exhibiting. The external conditions as well are important because at elevated temperature there is a possibility that the additive which is migrated on the surface can go back in the base polymer. That phenomena which is called as a reverse migration. Now, end application is, I would say, the key factor because that helps us to speculate the dosage level. So overall, each component here plays a very important role in order to ensure that there is optimum amount of additive present in the end application and we get the maximum benefit of the product. Now, in case of incorporation of this particular additive, we recommend to use a master batch route. This can, of course, be incorporated during the additivation or by any suitable compounding process. The idea is the additive has to be mixed really well in the polymer matrix uniformly. Now, depending on the base polymer, polyolefins as well as PVC, what we have understood is FinaGuard AM is working beautifully in case of both non-polar polymers as well as polar polymers. So we have conducted testing for polyolefins and PVC. However, we believe that it can very well work in other range of polymers also. So in case of polyolefins, the suggested dosage level is between 0.3 to 0.8% in the end application. This may vary if we are talking about extremely high crystallinity. So the end application becomes the key here. In case of PVC, we are looking at a dosage level between 2 to 3 pHr in the end application. And again, as I mentioned, we have tested this in polyolefins and PVC, and we believe that this can work in other polymers also at suitable dosage levels. So overall, FinaGuard AM becomes extremely appealing for various reasons. Definitely, it's not that the rest are not effective and only this product is working well. I would say this is bringing a multi faceted advantages, so when you're talking about naturally derived product, it's green, it does not contain any toxic components, so I think that's a big yes. And secondly, we have observed that FinaGuard AM is able to work in film as well as molded application. So if we start listing down the application, I think we are talking about kitchenware, we are talking about, I don't know, cutting boards, mouse handle, mouse covers, or electronic covers, and everything and anything which can be molded, as well as packaging films for sure. In case of PVC, we are looking at the sheets, bathroom wear, and I don't know, there are numerous applications. So probably it's just that we need to identify, or rather based on your interest, you can find this particular product suitable for your interested application. So just to conclude, I think FinaGuard AM, we can very well say, is a well-suited product for all your safety, sustainability, and profitability goals. So we are happy to share about this product with you and equally excited to hear from you about the same. Thank you so much for your time, and thank you so much once again.
Thank you, ma'am, for the nice and informative presentation on antimicrobial additive.
Thank you.
Sorry, there was some technical hinge because of which we all got disconnected. Now, today's principal speaker, Professor Anup Ghosh, is a distinguished and renowned professor in the field of polymer science and engineering at Indian Institute of Technology, Delhi, India, and a fellow of the National Academy of Sciences, India. Professor Ghosh has over 30 years of research and teaching experience and has 12 patents to his credits. He is known for his accomplishments in the field of polymer processing and rheology, having significantly contributed to the areas of reactive processing of polymer blends and alloys, 3D printing processability, polymer packaging, and microcellular processing of polymeric materials. Professor Ghosh obtained an MTech degree in chemical engineering from the Indian Institute of Technology, Kanpur in 1982 and a PhD in chemical engineering from the State University of New York at Buffalo, New York, USA in 1986. He worked as a postdoctoral research fellow at the University of Pittsburgh, USA till 1990 and then joined the Indian Institute of Technology, Delhi in 1991. He is a recipient of Young Alumnus Award of Chemical Engineering Department, Kolkata University, and Meritorious Service Award of IPI Mumbai. He is a recipient of the Teaching Excellence Award by IIT Delhi in 2015-16. Currently, he is President-elect of Polymer Processing Society USA. He is a fellow member of the Indian Plastic Institute. He held the prestigious Reliance Chair Professor at IIT Delhi. He has supervised 30 PhD theses and over 100 MTech theses. Professor Anup Ghosh will be sharing his knowledge about nanomaterials, which can be used as a polymer additive. The presentation will cover innovative applications as well as issues concerning to nanocomposite materials, mainly processability aspects in the application of these materials and future aspects of these materials in comparison with traditional polymer additives. I now welcome Professor Anup Ghosh.
Thank you, Kunalji. Let me see, I share my screen. Which one? No. Which one shall I press? Screen.
संदीप
संदीप भी गायब हो जाता है.
Bottom, there is a screen, share screen, green color, bottom.
Can you see that?
yes yes
Okay.
Okay. Let me make it a full screen.
Yeah.
Yeah. Okay. So let me first thank Mr. J.R. Shah. I have a very high esteem, respect, and when he called me about a year back, I think at the end of last year, something that, Anup, why don't you give a talk on this? I was really felt honored and inspired by him that let me take this opportunity to bring this subject. This subject is very well dealt with it. But you know, there are lots of challenges, and let's see what I can do that. So I'm being honored to be the speaker of JAYVEE Organics and Fine Organic Joint Endowment Lecture of, of, of this year. I also thank Mr. Hariram Thakurji, Mr. Mukesh Shah, Mr. Kunalji, and also our IIT fellow members for giving me this opportunity to be here. I was, as a part of IIT Delhi, many times we discussed and all that to actually organize this JAYVEE Organics and Fine Organic Joint Endowment Lecture. I have part of it. I have invited speakers to take the platform, and today I'm elated that I am given this opportunity to do that. I will try to bring this subject from the aspects of application, processability, and bring future prospects. Let's see how I bring it. I wanted to mix it up with the applications and the technology behind it, and I hope I can do that job. Again, I dedicate this lecture for Mr. J.R. Shah because this title was given by him in the email. I was thinking, what is the title to be given? And in one of the mail, he had written to me, Anup, be prepared, and we are fixing a date, and let's give a talk like this. And when I told him, he said, no, he's mentioned that to you. And I thought this is the title which should be, and I kept it as is, the nanomaterials as a polymer additives. What I added is that let me divide this into application, processability, and future prospects. Keeping in view of our IPI members, student members, and all that, I mix it up with the applications and also the processability aspect. Processability is a very important aspect which I like to cover this. As I start with that, if you see the, let me see if I can make it a point. No. Anyway, so as you see that there are three pictures. All three are very important. When we say the nanomaterials and nano additives, nanofillers and all that, once they mix it up, we cannot see it after mixing. Okay. And you need to have a special characterization technique when you look at it. See, other fillers, you know, sometimes we feel and we feel it in the film, we see that whether it's a transparent or not, how the dispersion is not. The dispersion to look at it is a bigger challenge. And if you can look at it, some of these lines are even a few nanometers, and nanometers are not visible in the naked eye. That's what I like to say that. Okay. So this is just to show a glimpse of that what you can see that. Next picture, you know, one of my friends sent it to me a few days back from the campus, that if you have a lotus leaf and if there's a water droplet is there, and he was trying to tell me in the morning, he sent me this picture and he said, our life balance is like this. Okay. So you see that you till the lotus leaf, you'll see the water is going around here and there, not even wetting the leaf. This is a very unique phenomenon. So if you want to look at it, you have to go into the why does this happen? Okay. So you generate super hydrophobicity. because of the structure of the lotus leaf. So you see how nature has given us, there are lots of examples are there by which you can see that, how this nano materials and nano surfaces, nanoparticles are existing. And that's because of that. And this has a lot of implications and applications. I may touch upon it a little bit. Okay, and on the right hand side is a unique science, unique technology. Is a multi-wall carbon nanotube, which is the buzzword now, which used to be 50 years back of nanofillers, nanotechnology. Now nanofillers, and this survey, so I have taken one picture from Google to show that this is a kind of structure. People are looking at it. They're doing extensive scientific study. The Nobel Prize is given, and they are giving a property. So it's very extremely difficult to develop this kind of a structure or material or filler. And if you look at it, you look like a powder. Once you look, in some cases I can see that. Let me start with my department now. This material science and engineering department, I call it new. After 25 years in IIT Delhi, I'm saying I'm in a new department. It is give me a biggest pleasure, because I joined when it was a Center for Polymer Science and Engineering. And in 2018, we broadened it into Department of Material Science and Engineering. Now we cover every aspect of material from polymer, polymer being the biggest particle. And then there is a metal, then there is a functional materials, nanomaterials, electronic materials that's being covered. I'm happy to share with the picture the day our department was inaugurated, and you can see our director is inaugurated that. As a part of that, what we are covering is all these, you can see nanostructure materials, electronic materials, ceramic material, composite materials, materials for energy, soft materials, biomaterials. We also have a center of excellence because of our persistence research, and we can say that among all institutions here, and we are in at par with many international universities and all. We do work on advanced polymeric materials. As a part of its recognition, we got a center of excellence uh, uh, award given from this Department of Chemical and Petrochemicals. And now with the new program, we are starting with both UG and master's programs. So we have a undergraduate program in materials engineering, master's program in polymer science engineering and materials engineering, and we have a PhD and master's program, and all of them. Let's come to the subject now. I like to start, if you look at ancient India, this iron pillar of Delhi, many of you have looked at it, have visited it when you visited Qutub Minar, and it is never rusted. So if you see that lots of study have been done in a one publications, I think it's a long years back from IIT Kanpur, it shows that it's the presence of nano level passive protective film of phosphorus and ferric oxide. Okay. So at that time, people knew how to make these nanostructures, and that still is there, and it's become a kind of a wonder that how it is happening. And if we look at, so that from that time onwards, even the Nobel Prize winner Robert Kurd said in 1996 that Indian craftsmen knew how to use nanotechnology. Let me bring it back a little bit. I cannot see you. Nanotechnology in lots of paintings, and carbon nanotubes they were using for these instruments, okay, to make this sword and paintings and all that. And this is still there, and that is maybe 2000 years ago that we are using it. If you think of spider silk, we know this silk material which is being used. Okay, if we just look at it, silk spider, we see that it's like a 5 centimeter scale. You are looking at it. If you take any one of the spider fiber, then you look at it in a different way, in a microscopic and macroscopic to microscopic to nanoscopic level, then you see that actually the spider is made of these nanostructures material, and in a protein and all that, you look at it in an angstrom level, and that is actually being used for developing lots of very beautiful sarees that are being made, and it is actually used by the nano level these fibers, and that's why it has so much of strength. And you know that the silk spider strength is very strong, and that can be used. If you see 35,000 BC, this is a famous drawing in France, okay, in the Chauvet cave, and where, lots of this has been used by the lots of pigments which are made from iron oxide, manganic oxide, carbon black, which are actually in the form of a nanoparticles. And these nanoparticles, in different countries, the people used to develop from the shoot of the oil lamp. I'll show you some of the some videos there. Okay, these actually contain nanoparticles. So we all are using and we are actually manufacturing it. These nanoparticles. So these are all pigments. What you can see that. Okay, they can be of any level, micro level to nano level, and as you go to the nano level, their dispersion, their property, their stability, their durability, all is going to be increased. So we should know how we should use that. I thought I will take this example. Very recently I realized that none other than my mother used to make actually the nanoparticle. Okay, it is the way she used to make what we call kajal in our cosmetics and this industry. So when we burn this, and I'll show you a video, and this is used to be put on the eyes and for the baby especially and all that. You can see that this eyeliner is known, and when it has been scientifically studied, it can be seen that it has a nanofiller. So now I remember that I have seen my mother used to do that on this kind of a the lamp that is being done. So if you look at it, this video maybe. So you see this these nanoparticles what we used to develop by ourselves at home. So it was kind of a homegrown technology which has been used, and that has been used as, and it found from the lots of studies have been done which shows that it contains carbon nanotubes, and that's what they were using in the other countries also, and in our old age practice which has been used. And this has been, now you can see that why I use that photograph there. So that has been used in a development what is called carbon-based spintronics, which has been reported by IIT Kanpur in 2007, and that has been used for developing lots of chips and elements where you need that spintronic devices, and that actually is actually coming from there. Obviously, the technology, the vapor-grown technology, has been developed in a very high level technology now, from that level to be used as a nanofiller, and these multi-wall carbon nanotubes are becoming very important nanofiller for the polymer additives also. So this is known, but let me tell you that when we go from meter to nano, we go by a 1/1000th of that unit. It is that meter to nanometer is 10 to the power minus 9. So if you see the scale, okay, so you reduce to nanometers, okay. So you reduce from 9 order of magnitude, you go by 10 to the power 9 minus 9 scale, and then you get what is called the nanoscale, and that's what I marked it here, that you get a 1 nanometer level, which is DNA. We can get 5 to 10 nanometer level where you get a carbon nanotube. You get some transistor is 35 nanometer. The proteins are about 10 nanometers. So in the scale of anything up to 100, 10 to the power 2, what I have put it in nanometer. So that is actually what is all in the nanoscale. And then even our blood cell and the sand grain and others are much larger, so that's why we can see them, but the nanoparticles is so small that we will not be able to see with our eyes. So what we'll cover today is the nanofillers. Nanofillers belonging to nanoscience and technology. In the nanoscience, we do discovery and study, which we are doing. Nanotechnology, we are developing all the products and applications. These nano composites are being developed by these nanofillers, these polymers, and these nanofillers. It can be of many different kinds, which I'll be explaining now. Okay, we develop through processing nanocomposites, and it can be of many different applications which are being used. There are a number of nanofillers, mostly are inorganic. I will go through that. These are very common. Nano clay, I'll give a lot of example. Fullerenes, carbon nanotubes are of and graphenes. These are the other group of nanoparticles or nanofillers that are coming now. uh, lots of nano, and the nanofibers also is becoming very, very common for use, and lots of application developments are being targeted and being used now. So these are the building blocks. From there we can develop that. This I have shown at the very beginning. I explained to you. Only thing I have to show now, that if I analyze below this water droplet, you will see that this kind of structure. This what we have to see. This we fail to see. And that's why, and these are called nano level. Let me see where is my pointer. These are called the nanoscale hair-like structures, okay, on which if you put a water droplet, so there is something called like a contact angle. So this contact angle is such, if you know this to have this surface up to this contact angle, you will develop hydrophobicity. If you do that, you can develop, these are called nanotechs. Nanotechs is developing this lotus leaf effect type of clothings, okay, on which if you drop anything, water or anything, there'll be no staining, because these surfaces are also exactly the surfaces like this lotus leaf, okay, and these surfaces, because here is a fiber, so here is a continuous structure, here is the same nano level fibrous structures in this clothing. And if you put any water drop, any other kind of liquid and all that, you see the shape of the droplet with the measuring contact angle or hydrophobicity is same as the same here in the what you see in the lotus leaf. So what we develop, the scientists, what we have to develop, we not only develop fiber, we have to develop a surface which have this nanoscale hair-like structure on the surface of the fiber. If we can do that, you don't have to wash your clothes maybe, because nothing will be coming on that. You don't have to have these. Today we need antiviral, antibacterial, this kind of surfaces, so it will not stick to that. If we have this material, it will be best for our PPEs and all the things which are developing, the front runner for even in this pandemic situation that's it happening. Okay. So it's a diverse application, which I was saying, nano electronics, biomedical application, textile, I just mentioned, automotive, food packaging, sensors, water purifications, and all that. I will show some of these applications in that. Now, how do we know this macro to nano? This is a very famous, the top one is a very famous photo. See, this is, anybody could identify on the macro, what I've written is actually gold. It is actually gold pictures, from which we I don't know where my, okay. So this gold picture is, gold is actually where we make jewelry, okay? And this is of this color. If we make this gold into a nano shape, so what you see on the right hand side, this color totally changes. So this is nano gold, and this is our regular macro gold or micro gold. So if I convert macro gold into nano, and then you disperse it, you see a color which is totally a different color, okay, which has been studied by scientists and published in iNano thing. So the color depends on the size, because when you see a color, it depends on the light, how it is being reflected from that surface. These nano golds are such a nano level structure. The light can pass through that, and your reflection will be different. And based on that, the color of the nano also will be different. So if we make a ornament jewelry with the nano gold, it will not show shining gold. It will show this color. Okay, so that's very interesting. Here, what I have shown comparatively, what I have shown to macro filler or macro powder filler to a nano filler. So exactly that happens. If you see the color of this, and this is actually the clay, which is actually looking like a powder macro filler, in which the nano size particles are hidden into that. Okay, and if you don't, this is what I'll be bringing to you, that if you don't disperse well, this remain as a macro. So you use a nano filler, and you will never see that it's a macro. Okay, so what we do, what we need to do is to develop technology by which you can disperse this particle, okay, and then it becomes like this size, and then either it may become even a transparent one. Okay, so better you can disperse, better you can separate them out, Okay, this will give a different property, and each and every one is a nano level, which has been looked into by transmission electron microscope. You can see this. So there is a the sea change in the color and the morphology and the structure as we change. Okay, it has nanofillers for many years had a significance in plastic industry, many years, but we could not catch it up. We are sometimes find it difficult. We sometimes are shy away from that. Okay, it is understood to be additives as in a solid form and which can give improvement in any mechanical properties and also in physical properties, but we have to be nano. Please remember that. Filling some certain volume and disruption of the polymer matrix, and it immobilizes some of the polymer chain along this nano surface. That's what we have to understand. That's why we say that if we can use nanofillers properly, we changes its modulus. You'll see that your modulus changes by 2 times, 3 times, like that. Okay, and it makes something rigid. So its a thermal property also changes. Okay, and the reinforcing effect of this failure is actually depends on the what type of nature of the polymer matrix and the filler, what type we are using, what kind of concentration what we are using, what is the aspect ratio. So filler is just not saying will do the filler. Okay, so what I shown you earlier picture, if you see aspect ratio, which is a one dimensional to the other dimensional, either the diameter versus length, diameter as a diameter or length ratio. Okay, or length by diameter ratio, whatever let's put it, length by diameter ratio. So it has to be maintained. So it is a 2 order of magnitude more. Size, obviously, orientation is very, very important. Okay, if we can orient it better, we get a different property, and then obviously the distribution will be one of the important factor. And how they work, they develop what is called an enormous increase in interfacial surface area. Okay, and we have to catch this surface area. Every surface area is actually working with the polymer chain, and then they make the total bulk polymer or the composites in a very high performance polymer nano composites, but with a very low loading of nanofillers, which you'll see. And that is the reason these nanofillers becomes very unique. It remains significant. And I will say the last 2 decades, the application of this nanofiller has increased tremendously. What is the advantage of nano? If we say micro or macro composite, because many of our fillers are like this, simple macro level. Okay, at the same level of loading, if I put nano, it will be even smaller than that, distributed well, much smaller. Okay, and their dimension, at least one dimension has to be less than 100 nanometer. Otherwise, it's not a nano material or nano composite, which you can see. So let me go by that. So what happened? So surface is to volume ratio has to be controlled. There is a percolation, okay, between how you distribute, how you connect them, that is, and they will give an exceptional properties. And I already mentioned some of the nanofillers that actually giving these properties. Now, if we look at it, you look at the change in the modulus, okay, it's a modulus of the nanocomposite divided by the modulus of matrix, which you can see as a y-axis, and the percentage of filler you can see has been given as the x-axis. The one of the line is for the nanocomposites, and another line is for the glass fiber reinforced polymer composites. So if you look at it, see, if you want 2 times the modulus change, you need even almost like 4 to 6%, not even 4 to 6, about 5% maximum of the nanofiller. But in the same thing, if you want to obtain, you need 20%. So whatever 20%, 30% glass fiber is giving the property, the modulus change has been given by even by only the 5% of, or even less than the nanofiller. So what is this? The modulus increased by ratio by 2, the glass fiber requirements is actually increasing by 3. So if we can control this, if we can go for nanofiller, what we can do by reducing from 20% to 5% or 6%, we are doing significant weight reduction in the composite, nano composite, and that may do with the fuel savings and cost reduction. I know there is a debate will be for the cost reduction. uh, we will work on it. If we can do the controlling the processability, and as an addition, you have a lot of other properties. I said there will be exceptional properties, that better surface finish and all that. This is a graph we generally show that as the particle size is decreasing, decreasing, decreasing. So 0.1 means 100 nanometer, zero point zero 0.01 is 10 nanometer. You see that the surface area is increasing exponentially by this process. And our job as an engineer, technologist, and chemist is to how to exploit this surface. Okay. So what do, sorry. So what we get? Better mechanical properties, as I said, better thermal properties, better barrier properties, and that's it is known for. Flame retardancies, another properties what we can do. Better improved abrasion resistance. Okay. You see that in tire also it is being used, and it will see that better optical clarity, and lots of work has been done nowadays going on biodegradability. So if you have a nanofiller with the polymer, it actually can make it more biodegradable. That is also been done. And these are the different structures of the nanocomposites and the nanofillers. You can see that, and we can look at it by electron microscope on this manner. So these are different pictures of silicates which are one-dimensional. You have a nanotubes which are two-dimensional. You can see I've already said that this aspect ratio, you can see that is very high for nanotubes, okay, in the ratio of 10 to the power 6, okay. And then there are some silica post materials. The carbon nanofibers is becoming very common, and the silica particles is being commercially exploited quite a bit. So based on these structures, we define these nanofillers in um, one dimension, zero dimension, one dimension, two dimension, three dimension, and we must know that. And then we can play with it, that what kind of orientation, what kind of structures we'll be using. So one has to select from different applications what are the things needed. I showed you these nanoclay structures in my earlier slide. So these are actually montmorillonite nanoclay which are being used, and now these are becoming very readily available and quite comparative price. I will say that compared to some of the particulate fillers that we are using nowadays. Okay. And you have to remember that once we are using this, we have to use much less than the microfiller. So there's a win-win situation with this nanoclay situation. But if we look at it, it just look like a powder. It's like a clay. It's like a mitti. That's why they do that. If I look at it, once I get this material, I look at it very carefully and analyze. If you look at it, you will see that if you take this clay and look at the morphology, you will see this look like a stack of layers. This is very important. And this is what I'm going to present in next few of my slides. Okay. What is important is this thickness of this layer. And what is important is the spacing between these two layers. These are all hidden into these fillers. The other fillers, they don't do that. If you take calcium carbonate, and even if you take nano calcium carbonate, if you take talc and if you take nano talc, okay, and you take nano zinc, you take nano magnesium, they'll all look like that, but they have a spherical structure, but this clay has a layered structure. And this layered structure play very uniquely. And each, if you see that, and each platelet is, you can see that 1 nanometer thick, and they have 200 times the width. So you can see already you are playing with an aspect ratio of 200 easily, or even more. And they have, each platelet has a high strength and stiffness, and compared they make it, bring it more rigidity into the polymer systems, and that's why we have seen the modular stage like that. This is the structure. So in these layers are actually, if you see, then they also have a very kind of a structure which is a combination of tetrahedral and octahedral structures, and then they have a exchangeable cations in between. This is another place where we can play with this. So when we have do that, so you can see that it is 1 nanometer. That's what I've shown here. And they have a D spacing, which is called a basal spacing, which contains this. And this gap and what is the cation inside these layers is very important. And we can play with it, our polymer and all that, how this polymer can go into that. Let me talk about little bit before I come to the clay also, that nanofibers also becoming very common. This I talked about this vapor grown carbon nanofibers. That's what I was telling about the suits, the kajals that we are preparing. That is actually going into 1 to 10 nanometer multi-layer nanotubes. And there are thread named pyrograph, which has come as a graphiting carbon nanofiber, which is 70 to 200 nanometer in diameter, and the length is in micron. So you can see that it is multiplied by almost like a 500,000 time aspect ratio. If you take carbon nanofiber scanning electron microscopy, you look like this. Otherwise, it looks like a powder. Okay. And if you take a TM, very high resolution microscopy, then you see that it's like a tube, but it has a hollow core inside. So you can if you can do that, a lot of applications and technology based on that, you can develop a superior properties. And then you can, and this is what has come now as a carbon nanotubes, which have become very common, as I said. And then we have in carbon nanotube what is called single wall and multi-wall carbon nanotube. Single wall nanotube is very difficult to generate. Single wall nanotube is very costly. It is still in a I'll say in the research level, which you can do. But multi-wall carbon nanotubes are becoming more available, and we are using it for many applications nowadays. Okay. And they are like this, which I've shown before, and they can be easily developed in with the used as a for a development of polymer nanocomposites. I just took some data which I got recently from this source, and where it shows how this is growing. So if you see that this data shows, I was looking for some data which gives a little bit of prediction. So you can see that for this nanocomposite application with epoxy resin in thermosets was very common. Polyamide is the first polymer on which these clays were actually being utilized, and very effectively the product. I'll show you some applications have been developed. Polyethylene, polypropylene, especially for packaging industry and all that has been developed. So if you put it together, you see that almost like a very strong, slightly exponential growth, which is foresee for this. And if you see some of the prices, these are on US dollar price, and but I have seen that they are more comparable. When you think of clays are from $2 to $5 per kg, if you convert it also, nowadays you'll be getting even 300 rupees a kilo for the nano clays, and also for the but carbon nanotube will be a little bit higher. But as I said, single nanotube is very costly. These are representative prices, and compared to that prices, I see that industrially these prices actually reducing, keeping almost like a similar trend, and which you can do that. Also, growth rate for nanostructure materials is happening, all different minerals, materials, polymers, and new materials. New materials actually covered all these nanotubes, nanowires, and all that. And you can see that the growth is from 28 to 41%, which has been shown by 2020. This is the percentage which is growing on. So it is actually capturing a lot of market, and nanofillers will be overcoming a lot of regular fillers also. I'm going to little bit go into more into the science, but before that, these are, I don't want to spend time on this. There are like to show that there are so many companies who are actually producing all these graphene nanotubes, nano diamonds, and metal nanopowders, silver nanoparticles, um, multi-wall carbon nanotube, nano silver, nano size silver powder, the graphenes, titanium dioxide particles. So they are all some of the representative companies, they're already selling it, and they are actually being used for many purposes. Now, let me show pictorially some of the applications. We look for high strength to weight ratio. This is one of the example. Lots of electronic devices, lots of strength, stiffness, material. Even the bridges are now being made with the carbon nanotube application with the matrix. Okay. Also, lots of construction materials. They're using now nano, and they're using nano concrete. They're using nano cement. গরম জল sorry. Okay, you know, world is not only with the nano carbon tube, nano clays and all that. Even if you see our metal oxides, then you see that there are antimony tin oxide which are used for a lot of semiconductive EMI shielding and all that applications. They are used. Lots of aluminum used for, you know, for wear resistance and developing synthetic fibers. With titanium as a, you know, there's a white titanium nanoparticles, and these are being used for a lot of absorbing materials for this purpose. And then there is a this alumina synthetic bohemite, which is used for a lot of surface modification, which are used for transparency and flame retardancy. Magnesia also being used as a fire retardant materials, and as I said, that nano silica it gives a lot of durability, mechanical properties, and in the concrete. So these are also being used. If we look at the pigments, you see that when we're using nano titanium oxide, nano silicas, and nano silver, they can provide lots of different functions: anti-gravity, bacterial, easy to clean, fire retardant, scratch resistance, and all that. You know, that Amrita was also presenting some of the application of the fillers, okay, which are used for antibacterial purposes. So nanofillers improve efficiency and functionality. So if you look at it, uh, for the paints, so now they are using the nanomaterials. So now you see lots of applications. I see lots of advertisements where they are using the word nano and polymer in the leading paint companies and all that. Okay, actually they are using the technology and they are trying to capture the market by promoting that, and then they can use. Okay, they also can be applied with many surfaces, okay, for concrete, brick, stone, wood, metal, and glass. Okay, so they had be more compatibility and adhesiveness, and they can be used, and they have a nanostructure surfaces, some of them also having what is called nanopora structures. This is an example what is going on. This is an example what is going on with what is called nano house. That doesn't mean we are staying in a nano house, such a small house. This house is made of uh, uh, which actually is looking for a in the construction industry and all that, that we are going for new paradigm of living. We have some energy, heat exchange, lighting requirement. We can develop different aesthetics. They have a different life cycle and maintenance. We can connect it to the different sensors and connecting to electronics, so which controls a lot of weather and other atmospheric conditions. We have a special coatings which are given. Then we can give a thermal composites and increasing structures and all that. And as I said, there are also nano composite, which is actually reducing some material cost and the labor cost, giving a lot of properties and environmental load. And this nano house project actually investigating the benefits and risk of a lot of paints which are using nanomaterials. Okay, and they can be used for a lot of abrasion, weathering, and leaching property control for this type of thing. So we can develop a lot of this. If we look at it, as I said, the first nylon clay hybrid composite was actually prepared by Toyota Motors. Okay, well they did improve performance both in modulus and very importantly the heat distortion temperature, so that it could maintain its property for at very high temperature. And you can see that they have used lots. They have lots of application which is used for exterior panels, interior panels, step assist, and engine parts. And what has been done in some of their vehicles, they use the polyolefin and nano clay with only 2.5% nano clay. They have compared the property which they used to use with 15% talc and PP composites. Okay, and then they found, obviously because of that, there was a 7 to 8% weight reduction. they got higher impact strength at a low temperature, and they got much improved surface quality. So that's what they gone for this, and they have introduced this in General Motors. They have their vehicles in 2002, and they also did some side molding for their Impala Chevrolet, and also for other things. As you can see that some of the bridges, some of the uh, protectors and the panels that have been used, and that has been developed. This has been developed by Toyota company, and they show 70% higher tensile strength modulus, 125% higher flexural modulus, and the heat distortion temperature also changed considerably. And this is because of this structure which has gone into polypropylene. So if it has been talc, it is a different structure. And now that it is nano clay, it is a successful which has been done even 15 years back when it was developed. We had worked with John Deere tractors. John Deere company came and they said that, let me show you, that they want to change their these all metallic parts, which you can see in green parts, by a composite material which has to be lighter material. Okay, so um, so we had taken so that target materials, they had given us this project to develop what is called PP nano composite and should have a better flexural properties. We had taken up this challenge. We have done a lot of formulation development. One of the formulation with 0.5% nano clay, we got very good processability and cost. And what they have done, they have taken this formulation and then molded into the, actually this is the shape and the size of the parts which they are fixing at the side of their tractor, and which gave a optimum balance of mechanical properties. So one of the kind of a success stories that we could develop. But there are lots into that. It is just that we cannot just add polypropylene and nano clay and that we'll get these structures. It has to be dispersed. It has to have some reaction, which you can see that. We see a lot of nanomaterials application in defense. Okay, there are lots of rubber and nanocomposite track pin bush which has been used by our Arjun tank, which you can see that this is being used. It has been developed with the nano composites. DRDO defense is one of the area where they are exploiting this nano very well. Some of the camouflage nets, which you can see that camouflage paints, these are being used with the nanoferrites, pigments, with conducting polymers and polyurethane and epoxy resins, and they give a good hiding and stealth characteristics. They give a protection against visible, near IR and radar detection. One of my PhD students worked with me from DRDO to develop also some of these special composite material. Okay, and then they also can be used for the vehicle and manpower against enemy surveillance and all that. We developed some of the nanoparticles. Let me go back to the next slide and I'll come back most probably. Okay, so we need to have these jackets, the bulletproof jackets for soldiers, for our security personnel, in fact maybe for us also. And it was unbelievable when I started working with that one has to understand how the nanoparticles actually work on these polymeric fabrics or the textile fabric material that can protect. And we needed to design, we needed to do advanced fiber architecture, we needed to do matrix improvement, processing, quality, and lifetime. And this is what you can see, that if you test this, if you develop this kind of nano composites, and then you see that we measure by bullet what is the penetration of the bullet through this. And if you see this diagram below, it is little bit not very dark. If you see that, this gives what is called the penetration depth. The world norm, the norm is that it has to be below 25 millimeter. It should not penetrate more than 25 millimeter when the bullet is fired. You can see the most of the geometry that has been developed here as a part of the project, and many other scientists are working on this. They already developed that even in abroad. First work was done in University of Delaware in USA. Okay, and based on the combination of the fabric, we can stop the bullet not even having finally 5 mm penetration. Okay, and this fabric combination and all that was actually developed very indigenously by us. I'd like to go back now and to show that because of how do we get that? We actually took what is called nanosilica. And if you take nanosilica in PG, polyethylene glycol, you can see this is the silica nanoparticles. Okay, if we do that, instead of just like a polymer is like a shear thinning material, it actually becomes a shear thickening material. And this shear thickening material means as soon as there is a bullet is hitting this on this, so what we put, these nanoparticles in a solvent, we put it on this Kevlar material or in dynamo material, which is ultra high molecular weight polyethylene. If we can dispose on these, so what will happen when the bullet is coming, these all nanoparticles aggregates together. If you can show that, if they aggregates together and they become shear thickening, and they can immediately stop the bullet. And this has been proven already up to the shear rate range of the, let me see, I think there was some bullet range, what you can see that. So we tried with some ballistic experiment with the projectile velocity, where we need this kind of shear rate 10 to the power 4. We have already reached 10 to the power 3, and lots of development happen so that these nanofillers, nanosilica fillers actually can save lives and will be the very good protective device for the ballistic purposes. Okay, and this work is still progressing, and it not only stop or reduces the penetration time, it actually reduces the weight of this jacket from say maybe about 20 kg to it is bringing down to even 6 to 7 kg. It was very hard for the soldiers to have this very weighty bulletproof jacket on this. Another area of importance is if we can do this, if we take a polymer and disperse nanoparticles in this, what we call is EMI shielding, is electromagnetic interference shielding applications. What happens? So this shielding value has come from polypropylene and multi-wall carbon nanotube composites. This also has been done with our research work, which you can see that. And when you measure this EMI shielding, you can control these values which are required for very many applications. And this comes from the conductivity of this, which is coming into the nano composites because of the connectivity of these nano level carbon nanotubes connecting each other at a particular concentration. And what is very striking to see, you can see that even at 4% nanoclay concentration, you already got the highest conductivity that you want. And if we have to use have this conductivity with a carbon black or even a microcarbon filler, we have to go maybe about 30% minimum of the weight percentage that we have to use. So you can use that they can be used for shielding, clothing, many clothing purposes. You can have this kind of protected device even for the women who are expecting babies, because nowadays everybody is exposed to many kind of radiation. Everybody has to be professionally working. So this can provide a very good support for this purpose. I don't have to say anything when I see that Roger Federer using a racket which is containing the nanoparticles. So in the racket, and I think that's why he's winning. Yeah, he won 20 times, 25 times. He's having a Grand Slam champion. So you can do that. And also the Oscar Perrier bicycle was actually, they both have the carbon nanotubes in the racket, and that's why they get the high strength to the weight ratio, that kind of properties that we can do that. Okay. Now, how do we develop this nano composite? How do we include these nanofillers is a bigger challenge. It looks very simple. We say that, okay, I have an organic polymer and we have an inorganic nanofiller. I'm very used to it mixing fillers into polymer, and we have developed so many applications. But the nanofiller is a different story, is a different science to do that. Okay. Now, what we have to do that, if we have to do and successfully to do nano composite processing, so what we have to see, we have to look at the layers which I was trying to show you in number of slides. Okay. So that clay material, which looks like a clay, is actually inside. It is like a number of layers, which is difficult to break, and it remains agglomerated. And that's why we say that even few years back, many people used to tell me, I don't know whether you use a nanofiller, but I'm not getting improvement of properties. Many people, even my students, used to do research and tell me, and many people from industry also tell me, nanofiller is expensive and we do not get any properties what is written. How do we do that? So you have to peel off, you have to shear off, you have to do this interlayer region mixing. So if we look at it, so my clays, when I showed you the clays, it looks like this, and these are all 8-micron particle, just like a calcium carbonate particle. But if we can shear them, it is written shear here. If you can see that those stack of layers which I showed you earlier, okay, they start getting, by shearing, getting displaced, and this shear is very important. And once they do the shearing, I'll show you that there will be diffusion of polymer inside that. I'll have a better picture in the later one. So we have to do not only shearing, we have to bring the polymer inside, which is a bigger challenge. And we don't know. So sometimes we use nanofiller, and finally our product remains as like is a macrofiller. Okay. So this is what you have to look at it. Okay. What do you want to do that? Okay. There are 3 ways. Okay. One is that when we are doing, we do polymerization to get polymer. How do we get polymer? We do polymerization. We all know that. Okay. When we are doing polymerization, that means when we are starting with a monomer and doing polymerization, we can already add some clay particle. It is actually easier, but this process is as a more challenging and difficult to control. Okay. Let me see where it. So you have the clay, we have the clay, and we have monomer, we are polymerizing. So when you are polymerizing, you get this polymer chain, and this clay is in between. So you prepare like an in situ polymer nanocomposite by that process. What is the other way? This is also very common way people try. So that is what, that you take the clay in a solvent, we take a polymer in the solvent, we mix the 2 solvent because it's like a dilute solution together, and then you mix it in the solvent, then you evaporate the solvent, which is actually environmental problem, and may not be used as an industrial practice. It is not possible to use it. What is we are looking for is a melt intercalation. It is more challenging. I was trying to tell you that you have different layers. You have these interlayer ionomers, oligomers, the tallow material and all that. We shear, but we also want the polymer chain to enter and go through this interlayer distance. The red one is the polymer chain, which is going, and there are lots of modification you have to do that. Now, if we do that, we generally don't get always what we want. The very common is, this is called intercalated polymer nanocomposite. This is common because this is little better than the regular filler composite, a composite based on regular filler or additives, and not actually up to the mark of nanocomposite. What we really want to go is this exfoliated structure. Exfoliated means all of these layers are being separated, and polymer is being and is surrounded by all of the polymer chains, and the de-spacing, the gap between the chains, these layers have been increased, and this will actually give. So our aim is to reach exfoliated structures than the intercalated structure. But as I said, most commonly, many of the industry practices will bring it to an intercalated structure than exfoliated structure. We aspire even more than that. Even in exfoliated structure, can we orient the clays much more in a fashion, or the fashion the way I like to have? Okay, so you see the intercalated structure is this kind of microscopic picture. Exfoliated is this kind of, more we go this kind of structure, more we are approaching actual nanocomposite, where you get the property that we like to have. Here you can see that there is still some agglomeration of the nanoclays, nanotubes. You will see that when you look at it, and it needs a lot of focus, lot of work on that. So we do this in situ. I've already explained to you the polymerization of nanocomposites. I'm going very quickly. So you have a controllable particle morphology, high transparency. It can accommodate higher content of nanofillers. In solution blending, we can have a easy operating condition, permeability of gases, but this actually needs a removal of solvent, which can be an environmental concern, and then aggregation may happen. This is the way we do melt blending, and this is a very enormous job. Now, how do we do this shearing? To tell you very frankly, the regular mixing methods may need some modification or changes when you want to do that, because clay particle always will work as an agglomerate. This clay particle, as you can see, and I'm saying that this needs to be shearing, and then they become smaller aggregate. Once they become smaller aggregate, you have to make it even a nano level aggregate. And this nano level aggregate, when they're shearing, there should be polymer to be diffusing inside that. And to do that, we need to do the de-agglomeration, dispersion mechanism that should be working. And that's what we are trying by many shearing experiment. And one of them is the mixing element or the kneading element, which is generally used in a twin screw extruder. And then if we can do it in a proper manner, as you can see that in the interspaces between the two of the rotating screws, if we can shear them, okay, and then maybe we can de-agglomerate them more, and then we'll get a surface area of 700 to 800 square meter per gram that can be obtained for this type of nano size particles. Based on that, lot of developments happen. I believe most of us are maybe familiar with the structure. This is a schematic of a twin screw extruder. I'll show only one schematic of this. And this shows that from feeder to the vent to the exit, there are different level of element of the screw which can be designed and which can be actually connected in a modular fashion. And these kind of kneading elements, knowingly, we have to know that which kneading elements to be used in which block, and there are they can be selected, they can be used, and then they can give a lot of different. One of the Japanese companies, they have developed what is called a tech mix based on all these principles. So what they do, they add a additional shearing element they can add with the twin screw extruder, so that same nanofiller, okay. So Nanomer is one of the nanofiller, nanoclay additives, nanofiller. It has been used with a resin, which is a polymer. We can feed in, but the regular mixing happen in twin screw extruder section. Then they have a special section which can mix these nanofillers, and then this is being pelletized, and then you get a nanofiller based master batches. What is the advantage? We get a very good dispersion of these nanoparticles, and that enhance. How do you know that? We see the heat stability increases. We have seen that the mechanical properties increases, and we do not use any solvent. Obviously, industry practice, we like to have a melt mixing, and there is a cost effectiveness is there, but that has to be balanced with the composition and the price that we like to see. What we see when I was trying to show these kneading elements that is working there, okay, what we see, you want to understand that when we do shear, there is a difference between shear and extension, and both has to work together. In the mixing mill, mixing equipment, or extruder, or twin screw extruder. Otherwise, we may get a lot of nanofillers, but we may not be able to develop the right kind of nano composites. So what we do, by shear flow, we try to disentangle and orient these fillers and the polymer chains. And by extension, what we do, we like to stretch them. So if you look that, one is shearing, so one is shearing and one is stretching. So if you do stretching, then what will be there? So suppose you can imagine that you have your nanofiller in master batch particle. It is you have to do one more step before you have to make the master batch, because that's a very difficult job in a nanofiller with the developing master batch. Once you have done the master batch and then you are adding to the polymer, general practices we are just do the shearing. Only shearing will not do the job. You have to do the stretching, and when you stretch this master batch layer, this layer become very thinner, and finally it breaks down into number of small domains. That's what is happens. Okay, and that brings the mixing. So it happens in these kneaders, in this twin screw extruder, where what I like to show you that you can generate this kind of dispersive mixing and shear in such a way. Dispersive mixing means stretching and shearing in such a way that these nanofiller which is trying to mix will be able to flow, stretch, extend, and then what is called a breakup. This breaks up into number of pieces. So this breaking up is common from common master batches. But when it is breaking, you have to also exfoliate that during this. Okay, that is the biggest challenge for this. Okay, so you have to exfoliate. So you have to have the particles to be shear apart, and you have to platelets which has to be peel apart. So we have to have some kind of a force which can actually makes polymer and other material to go inside this nanoparticles layer, where the platelets will be like a peeling apart, like we peel something, we peel oranges, and then we do that, we see number of layers, and then it goes. So from this structure which is there in master batch, you have to go to this structure and finally to this structure. And if you ask me the way I look at different micrograph, this is still not the best nanofill structure that we want to do that. But there are technology nowadays that we can utilize this, and we can measure this. We have gone one more. I wanted to give idea that, okay, how do we know? Like in regular master batch, I know how it has been mixed and all that. So there are now the technology has coming up. One more thing I like to mention, that nanofiller mixing, not only shear and elongation, you needs a sonication also. You need a very high level sound energy for the vibration and to peeling off these nanoparticles in such a way so that polymer and nanoparticle mixing happens. So I'll just show one slide to show that lots of new developments happen, that with the extruder, we can put a both dielectric and optical sensor now at the die, so that when these nanoparticles are coming, have they been dispersed, have they been mixed, it is being, so this is what you can see on the right hand side. You see dielectric die with the optical fibers and the spectrometer which is connected near the die to tell us that how the dispersion is happening, and how much despacing, the opening of the nanofillers happen, and how much is the polymers connected with those fillers and all that. And this is coming from the fluorescent study of fluorescent analysis. This has recently been done couple of years back, done in USA. We had a similar sensor equipment connected, and we have done some understanding and research in that. So what you do, you study this fluorescent emission intensity for different. So you can do that for different amount of nanofiller. Here we used a clay cloiside 15A with polypropylene. We have used some malleated polypropylene. I'll talk about it, that you need a polar group development for this. And then we mix a little bit of dye as it goes through. You can see what are the changes in the peak of this fluorescent spectra that is happening. And happening. So this left hand side is at different residence time, and the right hand side has different MFI. So you're changing the grade and trying to see if the viscosity changes. Okay, then the nanofiller is going into that. Then how we can control the exfoliation or intercalation of the dispersion that is happening. So this is also possible now to analyze this, and these are the sensor-based technologies which has to be connected to the extruder like that. This is one of my slides which I cannot go without showing this kind of slides because I am a person in processing and rheology. So this is known to everybody that this is how the rheological flow is, which you can see is in a honey. And our polymer, I always look my polymer as like a noodles, and as I sharing how they start flowing. But most important thing is to look at it. I will not spend, because I can spend 1 hour lecture on this. You look at the red arrow, which is very important, that if we change viscosity versus shear rate, when you want to change, molecular weight affects it, pressure affects it, filler affects it, all increases it. Additives are available which lowers it, temperature viscosity lowers it, but nanofillers tremendously increases the viscosity, and this is one of the indication that the nanofiller is there in the polymer matrix. And this is actually another challenge, that we cannot mix very well. This red line can be moving, shifting based on the different nanofiller. This may be shifting in many different ways. I've just shown as a kind of a tendency. So one of the study, if you can see that this nanofiller, just we have added, if you look at it, you said that 0.25%, 0.5%, 0.75%, and 1% nanofiller. Okay, change. See the change in the viscosity is happening by 1 order of magnitude. Okay, and this makes a tremendous challenge in the processing. So those who are working with PP calcium carbonate, and if I give a nano clay into that, they will say, "Oh, my machine is not working. My machine is not working. My machine cannot do this processing." Because you have to understand that because of this structure development, there is so much of viscosity enhancement is happening. One has to control, so you have to do that. So there are attractive interface, there is a repulsive interface, and we want to do that. And this based on the chain mobility, and then that increase or decrease the glass transition temperature, and then this has to be interpreted in terms of incorporation of nanofiller by the viscosity change. It also changes the complex modulus, and with the addition of 10 to 20% of metallic oxide filler, there is a complex viscosity change about 2 times, 3 times because of the interaction, frictional interaction between that. We have to look into that. So it's not that we cannot process with nanofiller, but we have to understand this and change our process condition, process parameters, and also the requirement. These are different nanofillers, and very important thing, those who are studying on this, they understand with this cation exchange capacity, and this actually determine how well a nanofiller will be catching a polymer very well. And depending on the polymer, we have to select. Some will be good for nylon, some of them good for polypropylene, some of them will be good for ABS material, and we have tried many of these material. The Southern Clay product, I also wanted to mention that this is one of the very big company in USA, and Nanocore, which actually are supplying this nanofiller quite well. So how this nano clay works? So there, what we call it, an organic modifier. All of the nano clay, which I was trying to tell, that in between those platelets, there is green modifier. You can see that they are there. These modifiers actually make these things a better nano clay for dispersion or making master batches. If we take unmodified, we will not be able to mix. If we take a modified nano clay, but modified with which kind of organic modifier, this is very important. And these modifier stability is also very important. That's why we had a problem that if you go more than 200 degrees centigrade, some of these organic modifier may not sustain sometime. Okay, so we have limited our work sometime up to 200, 220, 240 degree. You cannot go beyond that, and they will make. So there is a surface. So we need a combination of surface modification of the clay and polymer matrix together, and one can play with that. So what we do, that we can find a recipe for some of the nanofillers that can be used. And then this is the challenge, that when this recipe is there, we generally make this kind of attracting moiety or the component inside the layers, which will allow the polymer to come in, and then the distance between the two layers will increase. I like to move. So take this example of nylon 6 and nano clay. So you see how nano clay, and in between how this caprolactam monomer has gone, and there's the in situ polymerization happen, and you get a best. And that's what the Toyota could do that, and do that. We can also do melt intercalation. You can take directly nano clay, and we can take modified clay with this organic modifier and then join together, and mix together or process together. So we can also get a nylon nanofiller, nylon nanofill composites that can be developed, which it has been done. All morphology, what we do, there is a number of, so we have this I have shown for general purpose, that from optical microscopy to scanning electron microscopy to light scattering, transmission electron microscopy, and there's X-ray scattering. They are all used. As you go down towards the right side, you are going more and more towards the nanometer level, and this is very important. So one of the X-ray scattering you can see on the right hand side. What is most important part is that 2 theta angle, which is actually following Bragg's equation, that even if you don't understand, you have to see this graph and see that where is actually I am seeing my peaks. The peaks between 2 to 10, I'll say that 2 to 10 is very important, and you can see that this enlarged section has been shown here, and you see that if you don't see any peak, then you know that clay has been dispersed, the nanofiller has been dispersed, and that dispersion which it will be showing, if there is a peak, distinct peak, that means that is not there, is not been dispersed well. So you can see that. So for this nylon 6 and polyamide, you can see that we analyze this section, and more you see like that, you know that the dispersion has happened, and this is one of the way to characterize, and among the many other techniques that can be done. So we have done by the nano clay. This gives a kind of oxygen barrier which is gone down to 82%. You can see that water vapor has gone down to also 82%. But if you see that as we use nylon to nylon nanofield composite, if you can see that only 3% loading has given Young's modulus change almost double, yield strength almost 3 times, but elongation of strain has decreased little bit. Obviously, you are using filler, but any other filler would have decreased the elongation even more. Okay, so these are the cast film which has been tried, and then their barrier properties have been tested. It has been, the study shows that when we are using only P polyamide and P, it is actually 40-20-40 micron ratio. But when you're using nano polyamide in the as a barrier layer, we can reduce by 10 microns. So 10% saving in the film weight is happening, and then it can save weight. Hopefully, it can save cost because your incorporation or requirement is only 3%. Okay, or whatever the cost may not decrease, but you see the performance of the barrier properties. That's what people are looking for, and do that. This is what the images of clay polypropylene which has been done. You can see that again we can take polypropylene, but what we do, we do that take as a compatibilizer what is called malleated polypropylene or malic anhydride grafted polypropylene, and that they can react with the clay and go into the with the polypropylene and this nanofiller, and we can get a very good structure, a very good nano composite, which is possible also for the polyethylene, which has been shown on the left hand side. And here also you can see 57% increase in oxygen transmission rate for polypropylene or polyethylene and nanoclay, and for different polymer, Exxon polymer has shown this for this much change. HDP has shown this much of, so 57% for polyethylene, 20% change for the polypropylene because of the structure which I've already shown. So this is known that they have all better properties I have shown. So what are the issues? If we look at this, that reducing size always cost money. That's why the nanofillers cost more. Okay, so nano clays 10 to 20 times maybe the cost of the tall. Okay, 5 to 10 times I have checked that with the silica and calcium carbonates. Okay, but just 5% addition of nano clay can increase the cost by at least 40%, and that should be counterbalanced by the property that has been developed. Dispersing particles into polymers and processing, as I explained to you, is very difficult. That may add significantly to the cost. Surface properties become very significant. So size reduces, unexpected effects of may happen. At high temperature, there can be deactivation of stabilizer. Very small size also leads a problem. So some of them are potential problem, can be health issues, but generally once we make a master batch, we do not have to think about it. But when you have to do an other level, we have to also see. And we generally, what we look at it, that there is a degree of freedom reduces for the polymer chain, but we can turn into as a win-win situation for these, and many of these products have been done like this. I have taken a few examples of some of the companies. The Reed Advanced Material USA are extensively using carbon nanotubes, carbon fibers, carbon blacks for electronic display, batteries, and supercapacitors. 3M is looking into a lot of nano additives application, and they are also extending to dental, automotive, electronics, and the food sectors for that purpose. DuPont is developing various additives and modifiers for agricultural, biotechnology, and food technology, and especially the nano TiO2 based additives, and which are going into the packaging technology. The Toyota, I have already talked about it, that with CNT they have developed. They are nanostructured amorphous material company. They are also using so many material. Henkel is using a lot of nano ceramics and additives for their metals and conductive inks and for their electronic domains. Lances is used a lot of nano silica with the nano, as called nanoprene, and that way they increase the dry road grip between 10 to 15%. And they have also improved the stiffness of the thread block, which has a very positive impact on the cornering properties in the wetty surface, aquaplaning conditions, and all that. Abrasion resistance become much higher, and it also increases the service life of the tires when we do that. There are examples. I was talking to some of the recent developments to my colleagues who are already involved in. Lots of barrier tube shoulders are being developed. Some of the application development happened with the SL Propack with a company called Kurare in South Korea, and they are developing TiO2 nanocomposite based tube shoulders. Okay, these are the tube shoulders which is patented. Okay, and these are mainly for pharma formulation. Otherwise, it loses aroma because that methyl salicylate actually reacts with the with the aluminum foil or the polymer that is being used, and then HDP gives a limited barrier properties. So this has been now tried with, especially I think this has been patented, and this will be coming into the market very soon. They were claiming that it is 1.5 billion market that will be used for the lamitube shoulders and other things. This is used very recently. It has come from nano zinc oxide. I'm very thankful to Mr. Shah sending me, and I thought it's a really, really good example of Tata Chemicals coming out with a patented technology on variant with the zinc oxide, which can be used for PPEs in face masks and others, because zinc oxide is known for these applications for this purpose. This actually, you can see that each particle in this zinc oxide is in the nanometer range, within the 100 nanometer range, which has been it has come in August 2020, which has come. And this zinc oxide can be also further used as a vulcanizing agents of the elastomer, antimicrobial, and UV absorber. And you can see that react with cross-linking reaction that can happen with the rubber and other materials, and also it can be used for this purpose. I was looking into this area and found that the Israel, they have this what is called the nanofiber mesh machine. So if you have a hand burn or something, You don't have to put medicine or burnal because that makes it very oily and your skin surface doesn't get regenerated very quickly. What they do, they actually spray nanofibers on the surface, which is a medicated nanofiber. And that they become kind of a part of the skin. And then this medicine works on it. And when it is recovered, you just peel off this nanofiber layer and your skin become totally regenerated and got back into the shape or the regular shape it has been. So these are the technology which is being developed. So you can see that, and this is what is called electrospinning polymers, and to develop into nano surfaces which can do this job. We have electrospinning set up in the laboratory. We're doing a lot of research, but this is a handy machine. I think doctors can use it to do this job with a patient and all that. This is a new technology with the nanotechnology which has come up with my colleague Professor Mangla Joshi in IIT Delhi. It has just come up. Most probably it is just 2 weeks back, which has been commercially publicized. It is called Acure. It is a copper based master batches which has been used for antiviral, antibacterial and antifungal properties. So you have a container where the water is being going through the filtration. This is what I say, the copper release technology we are using in old days. You can see there's copper glasses and container we like to have water. The same technology has been utilized in a much advanced manner with the polymer master batch and utilizing it. And I was talking to discussing with her yesterday, and she was explaining to me that how this can help. And this bottle and container will be very soon available from a company that her student has launched, which is called a NanoSafe company, which has been funded by Government of India, BIRAC, and which has been supported by IIT Delhi and FITT to do that. And this is a lot. They are just coming up. They also are looking for market, and a lot of potential is there. They are just a startup company. So even many people may like to contact them. They also have developed what is called a mask, which is called NanoSafe, because they have used some layers and nanomaterials on the textiles, and that has been used. And this was also launched at the very beginning of our lockdown period, which has been, I personally use this mask, okay, and they have been marketed and has been, and they can be washed 50 times for this mask, retaining its properties in that. This is most probably my last slide, which is shows as a preparation of nanocellulose. This is another important area. I did not go into much into that, but you can see that there's a fiber. You know, we have a full of natural fiber in our country. If we take the fiber and if we can process it, we can go to microfibril matrix to nanofibril matrix, and then the nanocrystal. This nanocellulose and nanocrystals has a huge market and huge potential is coming. So you can see that, and average 30 micron we have developed. There are procedures available using acid-based technology, alkali-based technology to take the lignin out of the fibers, and then they take out the cellulose part and all that. So we are doing by a green process. We do not use any acid method. This has been developed by one of my PhD student, and you can see that we have developed both for nanocellulose and nanolignin. Very recently, it is also a startup has come up from our IIT Delhi, which has been supported by the PhD incubation program at IIT Delhi, and we develop a company which is called Cellulogo Natural Fiber, which we have seen having a super absorbent property of at least, I don't know, about 10 times of the other absorbing material that has been used, and we are looking for also many different applications. So last conclusion, commercial success for polymer nanocomposite remained limited for many years, but I am seeing that it is increasing very recently with development of innovative formulation and products with superior properties. Performance versus cost, nanofiller 3 to 4 times easily, but you have to also think that consumption is 1/3 of the regular filler. So you have to do a balance. We cannot, to have a win-win situation we may have. Packaging film, I was saying that when a EV wedge barrier layer needs a 10 to 12 micron, if we use a nanofiller formulation, you need just 2 to 4 GSM, which can be converted into 0.2 micron layer. Okay. So you can see 200 nanometer layer. Okay, and that reduces the requirement, that reduces the cost. Scientific study is exhaustive, but predominantly it was related to polar polymers. Now it is extended to non-polar polymers. So when I talked about nylon, it is a polar material, and that's why Toyota Group was very successful at the beginning. Now you can do it with any material, okay? But we are not successful yet with the high performance materials, okay? Uh, yes, high performance materials in the sense that going beyond 230, 40 degrees centigrade processing temperature is very difficult. That's what I've realized, that we are yet to optimize this exfoliated structure, which I showed you. And we also need to synthesize thermally stable hydrophobic modifiers so that we can go beyond 200 degrees centigrade. When we make nanofiller based master batch, we need polymer, nanofiller, and compatibilizer or ionomer. We can make also nanofiber based master batches. And general rules behavior of nano composite is very funny. You know, I showed some rheology, but I do it another filler, sometimes I see an opposite trend. So it depends on rheology and understanding between interface. How the inorganic nanofiller surface is working with the polymer is the biggest challenge, and we still have to work on that. So we have to do need-based, filler-based technology we have to develop. And we cannot say that this doesn't work, doesn't mean whole nano composite or all nanofillers is not working. So we have to know each, and we have to give respect to the nanofiller, that we have to understand its surface, its chemistry. So I believe both polymer chemistry and polymer engineering technology, both are important for nanofiller. Both have to come together. Both the science and the engineering has to come together for this. I just like this. I always like this, the quote that education is what remains after one has forgotten, one has learned from school. Okay, so if you remember anything from my talk, I'll be happy that after the end of it. These are my group of students who always work. They go on replacing their very dynamic group. Some of them passed out, some of them are here, some of them working with me, and they're in different positions. Thank you very much for your kind attention. Thank you.
Thank you, Professor Anup Ghosh, for enlightening all the participants about the nanomaterial and its applications. I'm sure the information will be very useful for the development of different composite materials and applications. I would like to thank both the speakers for the nice and very informative presentations. Now we'll have question and answers. First, I'll take questions for Dr. Amrita Poyekar.
Sure.
Mr. Vasan Uchil has asked,
Yeah.
can antimicrobial be used for thermoset phenolic resin?
Right. Thank you so much, Vasan, for that question. Now, when we talk about typically phenolic or thermoset kind of resins, the process is slightly different. So there is a presence of cross-linking step in that case. So if we assume that there is going to be a surface migration of the additive, which is the essential step, if we can achieve that surface migration, then yes, it is absolutely possible. We would like to know a little more of the system though. Thank you.
Okay. Mr. Kumar has asked how long FinaGuard can remain active
Yes.
in the product.
Right. So, Sukumar, actually we wanted to take this question live because this gives us an opportunity to discuss about the migratory type of additives. Now, there was a separate slide on performance parameters, as we say. Now, theoretically, if we have migrated additive on the polymer surface and the surface is not disturbed at all, it'll keep on working. But it's not going to remain that way. Of course, nothing is perpetual. So, depending on how often and how severely the surface gets disturbed, the additive which is present in the bulk of the polymer is going to replenish the surface and we'll keep on getting the activity. Now, here in this case, polymer acts as a reservoir. So we have additive present in the polymer which will keep on migrating, and for that time we will get the functionality in the polymer. Now, if you ask me a quantification of that, it becomes extremely challenging because there are external factors playing a big role as well. So probably, Sukumar, it depends on the end application. It will depend on multiple factors, to be honest. So I think that answers your question well.
Now the question is for Professor Ghosh. Mr. Abhimanyu Tyagi is asking, sir, if kajal contains carbon nanotubes, so is it harmful to use or not?
Vimunno, it's a good question, but my mother put it in my eyes, and I know it was, and everybody, all for the child and women also, they are putting it every day, every time, and it definitely doesn't have any harmful effect uh, for that purpose. Otherwise, it would have been shown in a different way.
Okay, again for Professor Ghosh, the attendee has not given his name. Why exactly is it more difficult to disperse nanoparticles, and how does a higher aspect ratio help?
Yeah, I think in my talk, maybe he has put the question before, but if you see what I try to explain actually is why it is dispersion is difficult and how you like to achieve it. Okay, I actually try to give you a little bit of science and technology behind it. Each of those, my processability lecture should be 2 hours actually, if I break it up after this. Okay, because when it becomes finer and finer, you have to see, you take something in your hand, you try to shear it, you will reach a limit, because nano, you cannot see it. If you cannot see something in nano level, how do you shear it? Okay, so we have to develop a new technology. You cannot, we are actually doing it, but we are modifying or enhancing our existing technology in such a way so that we reach that surface. Our shear means what? The velocity gradient between each layer has to affect the movement of the layer. If those layers are so thin, so nano level, how do you do that? So you have to be very effective. And one of the thing is that nanofillers has to be attracted towards polymer. So if we can increase, if you can enhance the attraction, and if you do it sharing, you will be winning it. So that's why it is so tiny. You have to understand the dimension of it. Okay, if the dimension is 1,000 times bigger, no problem. If it is 100 times, the problem starts. If it is only 10 times in nanometer, you will be finding it difficulty. And when it is nanometer, that's why many people try it and they say, oh, I do not see any effect. So that is the reason. Aspect ratio is very important. And because of those who are working with the general filler composite material, you should know there is something called critical filler length. You can calculate it. The critical filler length is related to how much volume percentage we are attaining and what is the orientation and the property we are seeing. Okay. If the aspect ratio is high, the critical requirement decreases. These aspect ratio high means what? The length is very long and the diameter is very small in nanometer level. So they will be able to connect each other if you can mix it. Okay, so what that is called a percolation. So they can be percolated for mechanical properties, they can be percolated for electrical properties very easily, and other performance properties. So the aspect ratio is very important even in composite. Those who work with short fiber composite, long fiber composite, you are actually using aspect ratio. And when you go to nano, it's become very important.
Next question. I think most of the questions are now for Professor Ghosh. Mr. Jayesh Rambia is asking, once nanofillers are made into master batch, while using it in injection or blow molding, do we need to take any special care?
Yes, that is another thing, because there is, see, in master batch also it is, I believe it will be intercalated, and intercalated to the exfoliated level to go in molding process is very difficult. And then there is a velocity difference when it pushes into the mold. Okay, very close to surface of the mold, there is a kind of a temperature and shear, and as it is going to the center of the mold, it will be different. So there is a velocity gradient. So there will be kind of a little bit, I will not say aggregation, as a segregation of the nanofiller platelets in that, and how to control that. Okay, so most probably what we can do, we can add a little bit dispersant, something we have to think how we can put it into the master batch. So master batch going into the extrusion process with the nanofiller, and master batch going into the injection molding in the nanofiller. We may have to see that in the master batch the dispersion remains intact, doesn't get destroyed again in the injection molding process. Another thing, injection molding happens in much more higher, 2 order of magnitude higher shear rate. Okay, so viscosity goes down again because it is at 10 to the power 3 to 10 to the power 5 per second shear rate. Okay, so there also there will be a segregation will happen. So it's a good question. Jayesh will always ask a very good question. But we have to, I think you're making me to feel and think that how we can develop something in the master batch even more. So we have to have tailor-make master batches. Just to make master batches, what I was telling, we have to put more attention to that.
Question is for Dr. Amrita Poyar by Umang Shah. Antimicrobial additives are available for polycarbonate and other engineering thermoplastics.
There are definitely. In case of, I would probably answer this based on FinaGuard AM. Now, what we understand is it can work in polar as well as non-polar polymers. We just need to keep a watch at the processing temperatures. Now, when we talk about thermal stability of the additive, of course, it depends on which polymer are we targeting to use this in. There are, of course, a range of additives available, and probably we would like to work around and see if FinaGuard AM can be tested in the polymers that he is trying to look at.
Now, due to shortage of time, I'll request everyone to please send your questions, email your questions. We'll send you the email ID and they will send it to the concerned person. I hope it is okay.
Yeah, I think it is better.
Yeah, that's better.
Now, the last thing, the vote of thanks. It is a privilege and great honor to propose the vote of thanks on behalf of IPI Governing Council and Mumbai chapter. We are highly grateful to Sri J.R. Shah sir and Sri Mukesh Bhai sir for sponsoring today's endowment lecture meeting. Kindly accept our sincere thanks.
Thank you.
We sincerely acknowledge the guidance and support given by our Governing Council Chairman Sri Hariram Bhai Thakkar, Endowment Committee Chairman Sri Pankaj Bhai Shah, and other office bearers in organizing this lecture meeting. I am sure that all of you must have enjoyed this lecture meeting. Professor Anup Ghosh presented a very informative and interesting presentation on nanomaterials and its applications as polymer additive and future prospects. Sir, kindly accept my grateful thanks for sharing very useful information about the upcoming material. Dr. Amrita Poyekar presented a technical presentation on green antimicrobial additive for plastics. Ma'am, your presentation was very informative and useful. I'm sure many will try to use antimicrobial additive in their products. Ma'am, please kindly accept my grateful thanks for sharing your views. I'm grateful to Mr. Sandeep Shinde, the Secretariat of HO and his team for the successful execution of this program. Last but not the least, we thank pioneers of IPI for their efforts and blessings. All the mentors, VIPs, IPI members for joining this lecture meeting in spite of the busy schedule. Thank you to all and have a nice evening. Thank you.
Thank you very much, sir.
Okay, thank you.
Thank you.
Thank you,
Take care,
everyone.
all of you.
Thank you.
Thank you so much.
Thanks a lot.
Thank you.
Thanks.
Thank you.
Thank you.
Thank you, sir.